Okay, first I'd like to thank the organizers for giving me the opportunity to present this talk. This is the research that I did for my master thesis with my supervisor Klaus Kiefer. Okay, the brief overview of this topic. So the quantum gravitational effects are strong at very high energies, therefore, which are present in the very early universe. Therefore, we hope that we could find quantum gravitational corrections to the cosmic, to the CMB anisotropies, which is assumed that has been originated in the inflationary phase from quantum fluctuations of inflationary field. Therefore, we start with canonical quantum gravity. And for our case, we repeat Hamiltonian formulation for inflationary Friedmann universe, in this case, closed universe. Then the quantization of this will lead you to the Villa-David equation. In between, we also will introduce curvature perturbations. And I'll mention the important property, which is this, why is this important. Then we will treat this Villa-David equation by a semi-classical approximation, which allows us to obtain the Schrödinger equation for the perturbations, and also quantum gravitational corrections to the Schrödinger equation, which leads us to obtain this power spectrum for uncorrected and corrected cases. And finally, I'll also talk about possibilities to compare the results with observations. Okay, so I also want to motivate why we have to consider closed universe. So first of all, the recent Planck data doesn't completely rule out the possibility of having slight curvature of universe. Also, there is a current discussion about the correct interpretation of the data, and particularly the paper published in Nature very recently, the authors argued that from Planck data, the positive curvature explained the anomalous lensing amplitude, and it also removes the tension within Planck dataset concerning the values of cosmological parameters derived at different angular scales. And they argue that the closed universe is favored by more than 99%. There is also this chance that the closed model could explain the observed low amplitude of quadrupole and octupole modes. Indeed, in this power spectrum, temperature power spectrum plot, you can see that there is a deficit and lack of power in this region. Of course, one can argue that there are huge error bars due to cosmic variance, but still one can see the tendency. Okay, so as I said, we start with canonical quantum gravity. Let me just briefly give the main procedure, how we construct this theory. So we start with Hamiltonian formulation, for which we have to first foliate the spacetime into three-dimensional Cauchy surfaces, where Hij is the symmetric on the hypersurface, n is the Leibniz function, and Ni is the shift vector. Using this line element in the Einstein-Hilbert action and varying the action with respect to the Leibniz function and shift vector, we obtain these two constraints. The first one is known as Hamiltonian constraint, and the second one is known as diffeomorphism constraint. To quantize these constraints, the main procedure is to make them as operators, act on the wave functional, and demand them to be equal to 0. So the first constraint will lead to the Villa-David equation, and the second one to quantum diffeomorphism constraint. Also, I should point out that the Villa-David equation doesn't contain any classical time variable because of the reparameterization invariance. And later, I'll show that within a semi-classical approximation scheme, we can recover the notion of time. Okay, so for our case, we have inflationary Friedmann universe. The line element is given by this. The shift vector is set to 0 due to the spatial symmetry. And substituting this line element in the total action, which is sum of Einstein-Hilbert action and the action of inflaton field, we will obtain this Hamiltonian, where alpha is defined like this in terms of scale factor, and so we have two dynamical variables here to describe the background, and this p alpha and p phi are their conjugate momentum. This result, so in order to obtain the power spectrum, we have to take into account the perturbations of the metric and scalar field. So by doing this, Halliburton and Houghton already obtained that the total Hamiltonian can be decomposed into the background part and perturbation part. with the first order Hamiltonian constraints. This result obtained by Hallwell and Hawking is not gauge invariant. To obtain to isolate the physical degrees of freedom, Langlois used a method developed for the Hamiltonian with first class Hamiltonian constraint and obtained the gauge invariant form for this perturbation Hamiltonian. The Qn is the gauge invariant variable, Pn is its conjugate momentum, and Wn and Un are some functions of alpha and phi. To proceed, it is more convenient to write this Hamiltonian in another form and use conformal time, which is why we perform canonical transformation and get a very convenient and compact form for the Hamiltonian, where omega n square is given by this. And to check for the large wavelength limit, we obtain the result that is well known for the flat universe. Okay. As I said, we also have to talk about these curvature perturbations, and these perturbations have a very good, very important role, as those are conserved quantities during the evolution, and will lead us to obtain the power spectrum of CMB as soon as we obtain the at the end of and related to the power spectrum of the end of the inflationary phase. So we introduced this gauge invariant variable zeta BST. Usually in literature, zeta is used instead, but in our case, zeta is not conserved. It is conserved only for the flat universe. So to be able to later obtain the power spectrum for zeta BST, as soon as we obtain it for this gauge invariant variable, we also have to relate this to each other, and this is the result. Okay, finally we are ready to derive the Villa-David equation. As I said, we have to take the Hamiltonian as an operator and act on the wave functional. The first term in brackets is the background part, and the second one is the perturbation part. Here, to obtain this for each mode, we have used the ansatz, the following ansatz, based on the assumption that the perturbation modes do not interact with each other. Before applying the semi-classical approximation, it's more convenient to write it in a more compact form, which is why we introduced these mini superspace variables like this, and JB is the mini superspace metric. Okay, now we apply Born-Oppenheimer approximation. Before that, we make also this WKB-like ansatz. And we implement this approximation by expanding the function S, which is function of background variables and perturbations, the gauge invariant perturbation variable, in terms of powers of Planck mass. And then we substitute this in the Villa-David equation, gather the corresponding powers of Planck mass, and set them equal to 0. And at corresponding orders for the first, at NP to the 4, we obtain the following equation, which basically tells us that the background spacetime is independent of perturbations. For the next order, we obtain Hamiltonian-Jacobi equation for the background, which is equivalent to the Friedmann equation. Next, at NP to the 0, we obtain the Schrödinger equation for the perturbation modes which propagate on the classical background. So we obtain this equation, and by defining a wave function and using this in this equation, we can write the Schrödinger equation. And as I said, we can recover the notion of time, and by defining the time here like this, which can be given in terms of introduced in terms of this dynamical variable, or the background dynamical variable here. And finally, we obtain also quantum gravitational corrections. We obtain this equation, and then we can decompose this function into two functions. First one only depend on background part, and the second one also perturbations. And similarly, defining a wave function, we obtain this quantum gravitationally corrected Schrödinger equation. One can notice that there is a nonlinear term here, but it has been shown by Leonardo Chatenier and Manuel Kramer for the flat case, which is not very different from this, that this term can be totally absorbed in the definition of inner product. So this doesn't create any problems. However, for now, in this work, we just ignore this term, but later we will discuss this more properly in other work. Okay, now we have to solve this uncorrected and corrected Schrödinger equations, for which we make this Gaussian ansatz, and for the Schrödinger equation we obtain this. We obtain equation for omega n 0, and similarly by creating this wave function, we get this equation that needs to be solved. Okay, so we apply some slow roll approximation, which is consistent with data, and the conditions for slow roll are those. And introducing slow roll parameters, we can get a rather simpler form for the Wheeler-David equation, where omega n square is given by this. So we can clearly see that there is this contribution coming from curvature. And for large wavelength limit, again, we recover the result for the flat case. And finally, now we obtain the result for the power spectrum. As we see, it is given by the real part of omega n 0, which we find by solving the Schrödinger equation, and substituting it here, we obtain this. And the main difference here, one can notice that we have scale dependence for this case, unlike the flat case. But the main contribution is for the large scales, as we will see soon. Also, let us also relate the power spectrum for curvature perturbations to the gauge invariant variable, and it is given by this. And again, by taking the large wavelength limit, we recover the result for the flat case. Now, to visually see the main difference compared to the flat case, we see that for the large scales, we have quite significant suppression of power here. And finally, we also have a cut here, which is because of the finite radius of the universe. And quantum gravitationally corrected power spectrum can be written like this, where this PV0 is uncorrected power spectrum, and we have this tiny term appearing here, which is also scale dependent. And again, by taking the large wavelength limit, we recover the result that has been obtained for the flat case by Brizuela, Kiefer, and Kramer. And they have already estimated that this contribution term is very, very small and within the error bars. Therefore, we unfortunately do not expect to be able to confirm this by observations. Now, with respect to uncorrected power spectrum, so the angular power spectrum has the following form, where these delta functions are transfer functions, and those depend on cosmological parameters. To study this the Planck data, usually power law approximation is applied, which is consistent with the data, and is consistent also with slow roll approximation and single field inflation. In our case here, this approximation is based on the assumption that there is only weak scale dependence. But as we saw, we had directly entering scale dependence, and when we directly calculate this spectral index -1, we see that there is n appearing everywhere. Therefore, we claim that for large scales, where the main deviation from the flat model occurs, the power law approximation is not applicable. Therefore, we cannot directly calculate NS and the amplitude and compare it with the already provided data in Planck. So the only option is to use numerical tools to calculate this and fit with data and see how well it will fit compared to the flat case. And let me very quickly sum up. So we obtained Wheeler-David equation, used a Born-Oppenheimer type of approximation, which allowed us to recover uncorrected and quantum-gravitationally corrected power spectrum. For angular power spectrum, we can only calculate this by sophisticated numerical methods, and by employing a closed model, we showed that we are able to obtain a lack of power for large scales. And with regard to the quantum gravitational corrections, due to their smallness, unfortunately, we do not expect to observe them. That's it. Thank you.
Thank you very much. Questions or comments, please?
Thank you for the interesting talk. I'm interested in the problem of time. Can you explain, please, what becomes different in the corrected version, the eta parameter that you inserted, is it any different from the usual way of solving that problem of time?
I mean, okay, here. So, I mean, for normal quantum field theory in current spacetime, we have the notion of time, right? So when we are coming from Wheeler-David equation, we have somehow to introduce it and to obtain this Schrödinger equation, which we should obtain for these perturbations, right? Which is why we have to introduce it somehow, and we already, from this equation, can notice how we should define them in order to be able to obtain this equation. So we see that this is very interestingly can be given by this alpha, by the scale factor and the field parameters. We can introduce it. So it is in this theory, it is not fundamental. Time is not fundamental, but can be derived here by this. Yeah, I see.
Other questions? Yes. First, Daniel.
So you define this time as an emergent quantity to mimic Schrödinger evolution, huh?
Yeah.
Because it's not coordinate time. Okay.
Yeah.
Okay. So Schrödinger evolution.
Because it's not fundamentally there, we have to obtain it for this approximation, because we have a classical background and on top we have to have the Schrödinger equation.
I see.
Yeah.
Thank you. Okay.
And my last question.
Yeah, my question is regarding the non-unitary, non-linear term that comes about. Could you kindly, I don't know, where do you get that term from, and like, do you have any idea what it means, or like?
I think I redirect your question to Leonardo. He's the master of that, so I think he will very nicely explain how exactly you can get rid of this, because it's just a matter of redefining the inner product. So yeah, I think he can give more details about this.
Okay, thanks.
A very quick...
Yeah, so just very quickly. This term simply comes from the WKB expansion of the state, but what it means, this has been debated in the literature for a long time, and in my opinion, it is not a violation of unitarity, because when you absorb it into the inner product, the measure of the inner product is exactly the Faddeev-Popov determinant associated to that choice of time. So the physical meaning of that is simply a gauge fixing.
Okay, that's very nice explanation. And okay. So let's thank the speaker and all the speakers.